It is my pleasure to welcome you to this two-day conference, and our topic is, unfortunately, the regional inequality in Europe and the US. And we're really looking for new empirical measures and policy approaches. And so I am Mary Ann Feldman at the University of North Carolina, Chapel Hill, and this is jointly organized with Dirk Fornal and Torben Klar from the University of Bremen. And I also want to acknowledge Elise Polly, whom I think all the panelists have heard from and who has really made this organization and this workshop possible. And so I want to begin with just some motivation and to just show this graph, which I think is pretty stark. And so this comes from the 2018 World Inequality Report. And going back to sort of 1980, we can see that, well, in the US and Europe, we roughly had similar distributions with about 10% of the top 1% of the income distribution sort of equivalent. Let me just say that again, so that the top 1% had about 10% of the national income in 1980. And the bottom 50% had between 20 and 25%, very similar. And if we fast forward, what we see is that in the US, we have had this incredible divergence where the top 1% now controls about 20% of national income, and the bottom 50% controls only about 13%. Picture in Europe is not as dire, but it is still sort of a divergence with the bottom 50% controlling less income. Of course, these are national numbers, but I think it's important. We're interested in the regional distribution, which is much more stark. And so this is a graph from Torben, and it is based on Eurostat data. And this is looking at, for different countries along the x-axis, this sort of income disparity, the people who are at risk of poverty, and then how that varies within country for cities, towns, and rural areas. And so we can sort of begin to think of going down from this national level to regional level and to see these differential effects. I was surprised because Torben mentioned to me that the sort of data we have in the US is not as available in Europe to allow you to track these trends. Let me show you this stark map, which is from the Economic Innovation Group, John Latari. And this looks at a 10-year period from 2007 to 2016. And excuse me. We can see that there are certain areas of the country where we've had income growth. And these are predominantly large cities on the coasts. And when we look at the places that have income decline, this is predominantly regionally concentrated in the South and also areas throughout the West. And so, this map we could use to talk about any number of phenomenon, look at COVID hotspots or who is wearing masks in the United States. And so now we are on the verge of an election, and we can, we'll see a lot of sorting along these party lines. For this conference, our goal is to shed new light on this phenomenon, new empirical measures and new methods, and then also to propose new policy approaches. I think this is the most important question for economic geographers, regional economists to study at this moment. So our agenda logistics. So 2 days, it's rather early on the East Coast of the United States. We're going to run today until 1 p.m. Eastern time. And then tomorrow also start at 8 a.m. and run until 1:45. So just some logistics. Each session is going to have 2 to 3 presenters. Presentations will last about 25 minutes and 5 minutes of short Q&A. And then we'll end each session with some moderated discussion. One of the things I'm enjoying so much about all the Zoom meetings I'm attending is the chat function, which allows us to engage and make comments. And then also there is a separate Q&A function for questions specifically to the presenters. And we have a whole variety of new social media. So, you know, different handles you can use and places you can post and tweet and Instagram. And so we appreciate your help there. And so I think that is sort of the, thank you, the end of my slides. We're going to take turns moderating the sessions. And so I am going to be the first moderator. Let me just ask, we had great geographic representation in our registration. May I ask people in the chat to just put where they're from? I'm only able to see the panelists and not all the participants. And so we had tried to think of doing a poll where we could sort this, but it's kind of nice, and also appreciate participation from Asia, and just great to see the wide variety of places. We also, let me mention, hope that this will be one in a series of workshops we will do. So wonderful to see the places where people are located. Oh, great. I see a lot of friends. And so it's wonderful to have this participation from the community, and also wonderful to have newcomers and to welcome you to our community. So our first session is really going to set the stage. And so we have two papers. Cesar Hidalgo from the University of Toulouse is going to talk about regional inequality, and then followed by Tom Kemeny from Queen Mary University of London, who's going to talk about creative destruction and inequality in the United States. And so roughly follows our program. Are there any questions before we get started? I actually am so efficient that we are ahead of time. But I think let's give more time to the substantive presentations. So Cesar, would you like to begin?
Yes, my pleasure. So, first of all, thanks, Marianne, and all of the team at Create for having me here. I've always been a big fan of the work that you do and your team does. And what I'm going to do today is first I'm going to share my screen, and then I'm gonna talk a little bit about, economic complexity and inequality. And following what you asked me, Marianne, what I did is I did a bit of a compilation of a lot of work that has happened recently in this literature, and that's what I'm going to present today. So economic complexity speaks about differences in the sophistication of economic activities. It is about the division of labor and about the factors that allow economies to engage in multiple activities. Inequality is about the distribution of inputs and outputs among groups, defined by geography, defined by activities, defined by demographics. And recently we have seen the rise of a literature focused on quantifying economic complexity and using these ideas to explain differences in different forms of inequality. So what I'm going to do today is I'm going to begin by summarizing recent advances in our understanding of economic complexity, and then I will proceed to use these advances to explore the literature connecting economic complexity and difference in inequality. So first, I'm going to ask, what is economic complexity? And this is a question that, as some of you may know, I've been exploring for more than a decade, and it has been helped by COVID, because earlier this year, around March, I was contacted by people from Nature Review Physics. They wanted me to write a review on the field, and I spent much of the confinement period writing a review on economic complexity that is scheduled to be published later this year or at the beginning of next year. And as part of that review, I was able to develop a better understanding of what is economic complexity and how it relates to production functions, which are the traditional way in which we look at things in economics. So economic complexity measures, what they try to do is they try to measure the availability of factors explaining the geographic distribution of economic activity. Now you might ask yourself, well, what factors? Capital, labor, knowledge, institutions, what? But what we do here is, instead of assuming these factors a priori, what we try to do is to learn these factors a posteriori from data on the geography of activities. So what we're using here is dimensionality reduction techniques that are used in machine learning and artificial intelligence to learn those factors. So we're not going to assume that capital and labor and knowledge are the things that matter. We're going to try to learn vectors of things that explain the geography of activities directly from the data. So what I'm going to do right now is I'm going to try to build a bridge between the production functions that everybody knows and learns in undergraduate and economic complexity, which is, the literature that I've been engaged over the last decade. And the bridge is based on this technique, which is called singular value decomposition, which is the generalization of the idea of eigendecomposition that we know from linear algebra. So the idea of eigenvectors and eigenvalues, when you generalize it to rectangular matrix, it becomes singular value decomposition, and is what we can use to build this bridge. So this is quite beautiful. So let's get started. If we take a traditional production function like Cobb-Douglas, this production function, what it tries to do is try to explain how much output you produce as a function of certain factors that you have. For instance, the capital or the labor that you have, a certain constant here that would be the technology or the total factor of productivity. And if you're going to do this empirically, you're going to try to adjust these elasticities or these parameters that tell you how important each factor is in the production of that output. Nice and simple. Now, if we can generalize these production functions to multiple locations and multiple activities. So instead of having a single output now, we have one output per location C and per activity P, and we're going to have many factors, let's say M or N factors. Nice. Okay. And now the last thing that we're going to do here is we're just going to simply take the logarithm, because when we take the logarithm, we not only change uppercase variables to lowercase variables, we basically transform this into a summation. Okay, so we're going to say that the logarithm of the output for a location and an activity is equal to some constant and a parameter that we learned here, this elasticity alpha, times the first factor plus another constant and the second factor and so forth. So this is what we do with production functions. Now, this is where the roads diverge, because in the traditional approach, you are going to assume factors F1, F2, etc. So you're going to say these are capital, labor, land, knowledge, etc. And you're going to use data on these factors that you can try to collect, and statistical methods such as regression to learn those elasticities, those parameters that tell you how much each factor matters. Now, if you do approach based on economic complexity, what you're going to end up doing is like, what? I don't know what these factors are. So I'm going to use matrix factorization techniques, and dimensionality reduction techniques to learn simultaneously both the elasticities and the factors. Now, how do you do that? You don't do it using regression. What you do is you use SVD, which is the optimal way to factorize a matrix into factors. Okay, so people in linear algebra and fields of mathematics that are advanced have figured out that there is an optimal way to factorize a matrix, which is this SVD factorization. And for any output matrix, for instance, a specialization matrix with location quotients, of size NC, number of locations, MP, number of activities, you can produce an SVD decomposition of the forms U times S times V. Now here, U is an I went a little bit backwards, sorry. U is a matrix that is equal to the number of locations and the number of locations, so it's a square matrix, and these are the principal components. These are gonna be the factors that locations have. S is a diagonal matrix, and these are gonna be the elasticities that you're gonna learn. And V is a matrix, that is square also, and is proportional to the number of activities. Now, because this is a matrix factorization, what you can do is you can approximate any matrix with arbitrary precision using the vectors in sequence. So for instance, you want to approximate the output Y for for locations and activities using only one factor. Okay, well, what you do is you take the first column of the matrix U, you take the first vector of the matrix V, you take the first diagonal element of the diagonalized matrix, and if you only want to use one number per location and one number per activity, you cannot do better than this. This is going to be mathematically the best possible factorization. Now, you want to do a model that has two factors. Well, you add now the second vector of the matrix U, the second vector of the matrix V, and if you added all of the vectors, you don't get any residual because this is a factorization. So you model the full matrix. Nice. So now let's put these two things together. So we have the Cobb-Douglas production function in log form upstairs, and we have this one downstairs. And what you have here is that, well, these parameters alpha and beta, these elasticities are these eigenvalues that you learn, and the factors, are these vectors that you also learn, but they're split into a number for a location and a number for an activity. So if this number is high for both locations and activities, it means that activity is really present in that location. If this number is low, that activity is not present in that location. Okay, so to understand this, it might make sense to look at this graphically. So, okay, we have matrix here using the county business patterns for US cities. So this is cities in the US, these are metropolitan statistical areas, these are industries in Nikes, and this is a matrix of the logarithm of the location quotient of payroll by industry and location, okay? So it's an specialization matrix. This is when you factorize it, using SVD. You have a matrix U, a matrix S that is diagonal up here, and a matrix V. Now, you can grab only the first vector. So if you grab the first vector of U and the first vector of V, it's just one number. So remember, matrix, you multiply rows by columns. So you're multiplying one number by one number each time. You can transform these two vectors into a matrix, and this matrix already captures quite a lot of the structure of the matrix that you're trying to model. Now you use two vectors, you do a little bit better. You do three vectors, you do a little bit better, and you're learning these factors. Now you use 8 vectors, and you're getting pretty close. So the first, actually 4, 5, 6 vectors already provide a very good model for a full specialization matrix. Okay. So of course, if you get like to 16 factors, you get much better, and you might ask yourself, well, how good is this approximation? Like if you look at these matrices, because these matrices are kind of abstract, it's hard to know. So I'm going to use as a toy example another matrix, one that looks like Mickey Mouse. So imagine you are factorizing a matrix that looks like an image, and you want to use the same technique. Well, this is how it looks when you're factorizing using one factor, 2 factors, 3 factors, 4 factors, 5 factors. So you see, you very quickly start capturing the essence of it. So when you're going to, of course, use 50 factors, you're overfitting. But when you're with 5 or 6, you're actually having a model that already captures a lot of the variance, actually the maximum possible amount of variance, very accurate. What has this to do with economic complexity? Well, the thing is, economic complexity index or these other dimensionality reduction techniques that have been proposed in the literature are basically a summary of the first 4 or 5 vectors of singular value decomposition. Okay, so here you have a chart, with metro areas in the US. So you see, the economic complexity index on the x-axis, and here you see the first 6 SVD vectors, of a matrix of log of the location quotient or RCA. And there's a very strong correlation of around 86%. But the economic complexity index is still kind of like, that's nice because it puts San Jose, Silicon Valley very much to the right, it scores very well. The same with Boston, Cambridge. You also see Chapel Hill down here also does well, and there's a reason for that, which is that the economic complexity index also normalized quite well, for the sizes of locations, so it's a very intensive metric. It's a metric of capacity, per capita or per unit, rather than a metric that is too correlated with size, which the SVD has a little bit of that problem. The first component of SVD have a lot to do with size. The second, third, fourth components approximate things similar to knowledge. Now let's look at other example. Here you have international trade data. So here you have once again the economic complexity index. Here the first 4 vectors of the SVD factorization. And you get also a very strong correlation, so that's what basically SVD is doing, is figuring out the factors that explain the geography of economic activities. And what the economic complexity index is doing is reducing those factors to a single dimension. So it's kind of like one number that helps explain the geography of economic activities, in a way that it's compatible with, what linear algebra or machine learning would tell us. So let's try to connect this with income inequality. So a lot of people have been looking recently at, the relationship between economic complexity and inequality. And I'm going to look at a few strands of literature here. The first one is the one that focuses on, income inequality internationally. But then I'm going to look also at work that looks at inequality within countries and then between genders. Okay? So this literature started a few years ago. The first paper exploring this relationship was a paper by Dominic Harman, who's now a professor in Brazil. And in what this paper, what we did is, motivated by the idea of the Kuznets curve, we tried to see if economic complexity could add to this story. Because people are familiar with the idea of a Kuznets curve, this tells us that inequality rises and falls as, countries develop. But in theory, this looks very good. In practice, it's actually much more noisy. You need a lot of imagination to kind of like see this quadratic term here, like there's a lot of scatter. So when you bring this into, the data, here on the left, you have the Gini coefficient of countries compared to economic complexity. And on the right, you have GDP per capita. If you put a quadratic term, you do get a little bit of the curvature, but in reality, that curvature is not really what dominates. So there's a couple of things that I want to observe here. The first one is we look at 2 countries, Chile and Malaysia, which are similar in terms of GDP per capita and education. When you look at them on GDP, they kind of like vertically align. When you look at them in terms of economic complexity, they're kind of, satisfying the relationship much better, because it is the difference in productive structures, the one that is helping explain those differences in inequality. Here, when you look at GDP per capita, you have countries like Kuwait and Qatar, which are big outliers because they're very rich, but they're not developed. So then, they move to the left here, and they sort of fall into place, when you start looking at the relationship as a function of economic complexity instead of GDP per capita. And of course, the amount of variance explained is much larger, like around 60% versus 30 to 40%. So we created a pooled OLS model that looks at the Gini of countries as a function of the Kuznets curve, schooling, population, a lot of variables, and the economic complexity index. And what we find is that there is a very robust relationship across countries in which higher levels of economic complexity are correlated with lower levels of income inequality, controlling for a large number of factors. Also worth noting that it explains a lot of the variance. So if you look at the relationship down here, when you have ECI, you're explaining around 72% of the variance. And when you remove that variable, you go down to around 64. When you remove, for example, GDP information, you don't lose explanatory power. So it's not just the coefficients that you're interested in, it's also how much explanatory power you have in this relationship. And in this case, ECI does much better at explanatory power than any of the other variables. So why? Well, because by being a dimensionality reduction technique, it's not trying to measure a factor, it's trying to measure the combination of factors together. So this all of the above metric is sort of capturing a lot of things that would otherwise, would have to be accounted separately. Okay, so then the other thing that was done in that paper was that we use, ideas from this literature to create an index of the level of inequality that is expected for each product. So for instance, if you look at copper, you look at the countries that produce copper. And by looking at the countries that produce copper, then you calculate like a product Gini index that tells you, well, the countries that export this product tend to be on average, more unequal than the countries that export paper making machine parts. And we could associate a product Gini index to any product. And that allows us to look at the product space, which is the network of related products, from a different perspective. We could see that there are areas of the product space that are associated with high levels of inequality, areas of the product space that are associated with lower levels of inequality. And then when you look at the evolution of a country's product structure, for instance, like Malaysia, you would see that they would move into products that have lower levels of inequality. So you would expect inequality to decrease. When you look at Norway, you see that basically they grow in areas that are associated with high levels of inequality. So you could associate a basket of products or activities to a certain inequality level and have kind of like some sort of counterfactual or expectation value for the level of inequality that a country is expected to have given the activities that are present in it. Now, what's the story? And the story of this paper, I think it's based on two ideas. The first one is the idea that practice structures co-evolve with the inclusiveness of institution was not new. This can be traced back to the work of people like Harold Innis, or more recently to Acemoglu and Robinson, or Engerman and Sokolov. And the idea is that when countries develop, they develop around certain industries that usually are dominant. For example, in Canada, it was fur, and that helps explain a lot of the institutions and the relationships between groups that develop, because they develop in the context of people working on those industries. Okay, so institutions in some sense co-evolve, or if you want to see it a little bit more strongly, may be begot by the activities that are present in a location. So the idea is that industries are going to be able to succeed only if they find the right institutional match. So the institutions that, for example, work for a company in Silicon Valley, which people showing up at 11 a.m., being creative, and basically not worrying that much about safety protocols, is very different than institutions that might work on a mine, in which people had to show up in time and to be very obedient to certain rules, because you're not looking for the creativity, but you're looking, to operate in an environment that is very controlled and dangerous. So there's co-evolution between institutions and a productive structure is the one that we use to explain in part this phenomena. And there's people that then started to look at this relationship deeper, and I want to highlight two papers here. One from Lee and Wu, and here they look also at income inequality across countries, and they look at economic complexity, and here they reproduce what we find in the 2017 World Development Paper, basically the same coefficients and the same story. But what they do next is they start adding interaction terms, and what they find when they add interaction terms is that economic complexity, as it grows, inequality on average is lowered, but there is a mediating effect of education. Okay, so the effect is negative because economic complexity is able to reduce inequality when the stock of high-skilled people is high. Otherwise, it would not contribute to the reduction of inequality. Otherwise, you might see inequality actually increase with economic complexity. And that's interesting because basically it tells it's not just the practice structure by itself, but it has to be coupled with an high level of schooling. This was also explored by Chu and Huang. This paper actually came out like 6 weeks ago or something. It's very new, and they explored this relationship. Similarly, they also use interaction terms, and what they find is that the effects of economic complexity on inequality depend on these mediating factors like education, government, trade openness are the ones that they use. So as countries become, more educated, they are able to exploit, the effect of economic complexity in reducing inequality. But if education is low, then the effect actually of complexity and inequality would be the opposite, would be positive rather than negative. So that's a little bit of what we know at the international level. At the subnational level, there has been people like Margarida Bandeira and Angelica Sbardella and colleagues that have, looked at data in Brazil, look at data in the United States, and here they find a positive correlation between economic complexity and inequality. So that's interesting. So what might be going on here? And the hypothesis that we have been exploring with some of my colleagues is that, well, people are more mobile within countries. So since people are more mobile within countries, big cities attract a large variety of people. Like cities like New York and San Francisco, they attract, smart, educated people, but they attract poverty in certain ways. So what we might be observing here is what is known in statistics as a Simpson's paradox, which is that between countries, the relationship is negative, but within countries, the large cities like Berlin or Paris or Lima or Santiago in Latin America, are, cities that are very unequal, but between countries, the relationship is negative. So that would be a way to make these two things compatible. And one mechanism that could help make these two observations compatible is the idea that local mobility is much larger than international mobility. So people sort themselves within countries into cities, and that, makes large cities more unequal, but between countries, that sorting is much, much, much more limited, especially, nowadays, with the sanitary situation. We do have kind of like a bit of an observation of, well, what's the difference between these big cities or not? And this is a paper that we did with Pierre Ballam that came out on Nature Human Behavior earlier this year. And what we did here is look at the concentration of different types of economic activities using data on patents, on publications, on industries and occupations for metro areas in the United States. And to quantify this concentration of activities, what we did is to look at scaling relationships, which is how, the output of an activity in a location grows with the population of that location. So in most of these situations, this output grows super linearly, okay? So basically the per capita output grows with population in all of these different activities. But when we look at activities that are different, like neuroscience or arts and humanities, or computer hardware and software and pipes and joints, in the case of patent data, we find that these scaling relationships are different. Scaling relationships are more superlinear for activities that intuitively we would think are more complex. Unfortunately, here we couldn't use a measure of economic complexity that comes from the geographic distribution of, activities, because we're using already that, as one of the measures. So we use other ad hoc measures of complexity, like for instance, the average number of authors in a paper. So neuroscience, a very complex field, has a higher division of labor than decision sciences or economics. In technologies, we also use two different measures. How long ago was the subclass introduced? So old technologies like heating or pipes and joints are considered less complex than technologies that recently got, or more recently got, a classification, like semiconductors, or also using the average number of inventors. In both cases, we find that the concentration, like the scaling exponent, becomes more superlinear the more complex the activity is. We do the same for industries, using measures of education here as proxies for complexity, and here you have, like the same story, but told in a regression language in which we're looking, for instance, at the number of patents, that a city produces in a certain class, and we use the interaction between population and knowledge intensity as a measure, of the effect of economic complexity on the superlinearity of that scaling. And we find, that, these interaction terms are all positive and significant, meaning that the scaling of population is more superlinear, in this case by, it goes up by 0.12, the coefficient, when you are in the presence of a more knowledge intense activity, okay? The last thing that I'm going to touch upon is the relationship between economic complexity and gender. And here I want to highlight two studies. The first one is this study by Ben Saad and Azum Ella. And what they do is they look at gender parity, and they look at a gender parity index in education, in tertiary level enrollment, and primary and secondary level enrollment. And they find that in basic levels of education, primary and secondary, economic complexity doesn't improve gender parity, but they do find, you know, a relationship between economic complexity and gender parity for tertiary education. So this might be telling you something, that economic complexity is able to help achieve certain, you know, positive outcomes when it comes to inequality, similarly to like what Wu and Trang showed, when education stocks are relatively high. So they might be kind of like some sort of demand story going on here, competition for skills. And that's what we explore with Radu Barca, Christian Jara, and Martina Viarengo in this working paper that is now under review, by using data for all of the formal sector economy of Brazil. So we had linked employer-employee data, meaning that for everyone in Brazil in the formal sector economy, we knew where they were working, you know, who they were working with, what type of education they have, you know, which location they were working on, basically like a very, very detailed individual level data set linking employers and employees. So by using this individual level data, we could explore gender wage gaps in much more detail. And we found two things. The first one is that a lot of the gender wage differences are explained by sorting of people into different activities. So here we have all of the states in Brazil, and here we have coefficients, you know, that were determined using individual level data. Okay, so if we only control for individual level covariates, here you would have the gender wage gap that you would observe. Okay, so you would say, okay, in the state of Acre, you know, for every real that a man makes, a woman makes, you know, 12 cents less, you know. But as you start adding controls, for example, for the economic sector, or for economic sector and occupation, or for economic sector and occupation, these, you know, gaps reduce. So about 40 to 50% reduction. Here you see, like, zoom in. So you look at Minas Gerais, that's a large state, you know, there is $1 to 70 cents, you know, when you only control for individual level covariates. But when you control for, you know, the sectors and the activities that people are performing within those sectors, you go down to, you know, a $1 to 85 cents type of gap. Okay? But what we do next is we say, well, you know, is this something that is constant, or, you know, does the knowledge intensity of the activities matter? You know, so then we look now again at this relationship, but we start looking at interaction terms between female, the high skill industries, the high skill occupations, sorry, and the knowledge intense industries. And what we find is that females that work in high skill occupations or knowledge intense industries, they experience less of a gap, you know, than, you know, females that would not have those characteristics, meaning that they don't work on a high skill occupation in a knowledge intense industry. So what's the story here? Well, the story here that we try to tell is based on, you know, the classical theories of discrimination that suggest that firms choose workers based on characteristics that are unrelated to productivity. So firms that would choose workers based on race or gender had to pay a cost. You know, this is the cost of accepting people that is not going to be as good as the job as the women that you rejected, or the person from the minority that you rejected. But this cost is going to be larger for knowledge intense activities. So if you're looking at people, you know, to pack fruit, you know, in a fruit packing plant, that suboptimal matching might not make a big difference. But if you're looking at knowledge intense activities, not hiring a very smart woman because you're hiring, let's say, a smart man, you know, might, you know, be a larger cost. So since economic development is about the growth of knowledge, and we know that, you know, because of endogenous growth theory, the cost of choosing workers based on characteristics that are unrelated to productivity should increase with development. So if we put together, you know, Becker's theory of discrimination and Romer's theory of economic development, you know, we make an interesting prediction about the gender inequalities in wages, which is that gender wage inequalities should decrease with the knowledge intensity of an economy. So moreover, since this effect is driven by the cost of accepting suboptimal workers, you should expect this effect to actually be more noticeable among high-skill occupations in knowledge-intense economic activities. And that's what we find. Actually, for example, in Brazil, when we look at states that have shortage of high-skilled workers, those are the states in which the gender wage gap is reduced the most for, you know, knowledge-intense industries and high-skill occupations. Because basically, in that place, you know, you cannot hire a worker for or compensate a worker for a characteristic that is unrelated to her productivity. So this is interesting because it tells us that, in some sense, increase in economic complexity increases demand for skills, and those increased demands for skills generate incentives for creating institutions that are more inclusive. So just to summarize some of the things that I presented here today, recent advances in our ability to measure the complexity of economic activities have stimulated a literature exploring the relationship between economic complexity and inequality. We now know that economic complexity is about the factors that explain the geography of activities, but when it comes to inequality, we have learned a few things. Broadly speaking, we know that higher levels of economic complexity are associated with lower levels of income inequality, and that this relationship is strongly mediated by the availability of education and institutions. So it's not just increases in economic complexity, but increases in economic complexity coupled with a strong, outcome in education that, help achieve this inequality outcome. At the subnational level, there is some evidence of a positive relationship between economic complexity and inequality, which suggests a Simpson's paradox, and that could be explained maybe by higher mobility of people at the subnational level. So the fact that there is equilibrium, quote unquote, at the subnational level, but not so much at the international level, and that pushes large cities to become, more unequal because of their ability to attract, people from both extremes of the skill, preparation, and privilege distribution. Finally, when people have been looking at the relationship between economic complexity and gender inequality, one paper has found economic complexity to be associated with more gender parity in tertiary education. So once again, we start seeing this relationship between economic complexity and education at a high level of sophistication. This is not about, first and second grade, educational attainments, but actually about, university education. So that is interesting. And using linked employer-employee data for Brazil, we find that high-skill occupations in knowledge-intense industries, tend to show lower gender wage gaps. And with that, I would like to thank you very much for your time. Happy to talk a little bit more about this, in the Q&A session. Thank you.
Wonderful. And so really a great way for us to start off this workshop, and also a tremendous overview of your work and multiple papers in this developing literature. And so I appreciate you providing the background and then weaving this all together. But I would like to ask, from this, these are large data projects, right? And can you talk a little bit more about, sort of the organization of all these studies, the data that you are using, where you think we have the best data availability? And then also, Cesar, just to touch on some of the policy recommendations. I mean, I think your work, especially on gender, but also looking at how sort of the structure of the economy affects income inequality and suggests pathways for developments, is really powerful.
Thank you. So regarding the first question regarding data, I think there's a few sources of data that have been used quite a lot, and there's other ones that are increasingly being used. So international data has the problem that it has to be comparable. So for complexity, people mostly use trade. It is possible now for samples of countries that are not that large to use patents, and data of that kind to calculate complexity as well. And inequality data, it's hard to find. So you have to use the Texas data set, all of the Guinness data set from Branko Milanovic. Though basically, like, we're all building over the same things. That makes the results comparable, but at the same time, we're all looking under the same spotlight. So it's unlikely that we find something different. At the subnational level, that's where the data gets interesting. So for instance, in Brazil, we use the RISE data set. This data set is, a lot of countries have data sets for Social Security Administration purposes. And this is the RISE data set on Brazil. So everybody that pays Social Security taxes is part of that data set. And that provides a great view of all of the formal sector economy, because it's not a sample like a household survey. It is the universe of people that pay Social Security taxes. Of course, it's biased towards the formal sector of the economy. And in places like Mexico or Brazil, the informal sector can be huge. But at the same time, you wouldn't expect, even though you'll be surprised, people like doctors to be informal. Although we recently finished a project like Data Mexico, and we find that there's tens of thousands of, MDs in Mexico that are technically classified as informal workers, in the official records, which to me is surprising. But that's kind of like the types of data that we get to use. So I do think that there's two keys here. One is the data we've used, which is administrative records like Social Security Administration records. Those are very powerful. The other place where I think we might be able to find data that is interesting is in online repositories like LinkedIn, and the way to access that data is basically sending students to do internships to those companies so they can access it's easier to move people to the data than data to the people, and there's people that are doing that right now. When it comes to the policy implications, I think that's, it's hard because I'm quite convinced by now that economic structures do matter and affect a lot of things. But how you move them, that's something that it's really hard. And we have a lot of examples of successes and failures. So I remember in Utrecht, you gave a wonderful talk about, how in North Carolina, they actually were able to move, the proactive structure to one that is more knowledge-based with the research triangle. But that's one of the few successful cases that we observed, and we do have other cases like in Singapore and in Korea that there have been pushes that have been coordinated and they have been effective, but those cases are really hard to transplant. So there is another literature that has been emerging, especially in the last 2 years, of people putting complexity now on the left-hand side of the equation and trying to see, how do I move it? For example, Athanasios Lapatinas in Greece has been doing a sequence of papers on that and using instrumental variables to try to trace causality as carefully as he can. And for example, he does find, that internet connectivity helps, move like complexity a little bit faster. So we also have a paper looking at high-speed rail in China, and we do find, for instance, that acceleration campaigns of high-speed rail, they are correlated with acceleration of knowledge diffusion between cities. So at the end, a lot of these policies, might be policies of transportation, of communication, of education, things that we're used to, and we might kind of like start looking at how those contribute. Finally, there is another interesting literature that looks at institutions and demographics. So there is a paper in World Development by Dani Bahar and co-authors in which they look at the birthplace diversity of people, and they find that places that have migrants from many different locations also, increase their complexity faster, than places that get all of the migrants from the same 2 or 3 places, So birthplace diversity appears to matter. And other people like Wu, which I show a paper from him today, who has been doing a lot of work in New Zealand, he also has found that locations that are more inclusive of LGBTQ+, they also, finds kind of like an institutional effect on improving economic complexity. So that would be in alignment with like Richard Florida's ideas, on the cultural cluster. So I think people are looking into this. I think it's hard to have 1 or 2 levers, but I would say that we know more than what we did, like 10, 15 years ago, and that's good. Yeah.
Absolutely wonderful. And so, one of the things we hope comes out of this is a research agenda. And I appreciate your kicking this off, and you've given me some ideas for my own work. Our next speaker is Tom Kemeny from the University of London, and his paper is called Creative Destruction and Inequality and in the United States.
Hello, everybody. Thanks very much for the introduction, Marianne. And really happy to be here and part of this great workshop. So I'm going to, let's see, I'm going to share my screen here. And get started. Here we go. Okay. So, so this is work, very much, I should say, to start off with, a work in progress. And so unlike Cesar's work, which is, I would say, more retrospective, although at the end it was also forward-looking. This is really a talk that's about a project that's not in a sort of very well-determined place. And so this is a chance for us to let you know what we're up to and get some feedback. And so this is work that's joint with my collaborators, Sergio, Petralia, and Michael Storper. So let's get started. So the stylized facts that are motivating the work that we are doing have to do with inequality, of course, as befits this seminar. And in particular, we're looking at the United States, and there are two kinds of inequality that we are interested in trying to better understand. The first of those is what we might describe as interpersonal inequality, so inequality between people. And the second of those is interregional inequality, or inequality between, let's say, average wage levels between places. And the figure that you see up on the screen here is a visualization of the evolution of measures that capture both of those kinds of inequality. And so we've got measures of interpersonal inequality and interregional inequality measured either through a Gini coefficient or through 90-10 wage ratios. And I should say, when I'm talking about inequality here, I am talking about specifically wage inequality as distinct from income inequality. And I think that's an important distinction to be made in the context of the work that we're doing. And so what we see very clearly here is this trend from starting from 1940 to up to 2000.
Excuse me, Tom, we're not able to hear you. Tom, excuse me, there's no sound. We've lost the sound, Tom. So, right, somehow your sound has dropped off. Okay. So technical difficulties, we depend so much on this technology. So I think that Tom is going to log back in. But while that happens, we do have a question for Cesar. So Katja Kleinschmidt has a question in the Q&A. And so
yeah, I was about to answer it on the keyboard, but I think we can use the opportunity here to explore it. So thank you, Katja. I think this is a great question, and it's true that, you know, as economic complexity grows, this can be driven by the growth of like a few sectors that might themselves, you know, not be very gender inclusive, you know. And I think in the US, you kind of like experience a little bit of that when you look at the programming phenomena of, you know, of Silicon Valley and you know, and the tech sector, and that sorting between occupations, it's really where a lot of that difference is observed. Let's see, maybe Tom is back.
Hi, can you guys hear me now?
Yes.
yes.
Can you oh, the joys of online conferences. So yes, you can hear me. Oh, hello.
Yes.
Yeah. Okay, good. All right, let's try this again. So can I ask, where did I cut off? Did you hear any of what I said?
You know, I think it would be good to go to your second graph, which you were explaining, the one that goes back to 1940, which is just fascinating. And
okay,
that's about when it cut off.
okay.
Okay.
I'll try again. All right, let's see. Okay, I'm hoping you can see my screen now.
Yes.
Good. Okay, so, all right. So I'll start from the beginning of here. And so what we're interested in explaining is inequality, and specifically wage inequality. And we're interested in it at two different scales. One between people or interpersonal inequality, and another between places or interregional inequality. And so as a sort of an opening stylized fact here, we are tracing the evolution of both of those. To capture interpersonal inequality, in fact, we're looking within regions. We're looking at intra-regional inequality, but I could show you lots of other graphs that are sort of national interpersonal, and they look very similar to the intra-regional interpersonal stuff. And so the point of this slide really is across a whole bunch of different ways that we might measure it, and this is just a few. If we go all the way back to 1940, and this is throughout using census microdata, we see a very consistent pattern, which is these two sort of different epochs of inequality at both scales. Between 1940 and 1980, we see this relatively strong compression or decline in inequality between places. By places, these are commuting zones, but also between people. And then right around 1980, we see this sharp uptick in inequality. And so there is this sort of golden age to great divergence sort of pattern. And this is really what we're trying to explain. Okay, so of course, the discussion about the recent rise in inequality, this sort of 1980 and beyond kind of inequality, has been very, very widely discussed across a wide range of disciplines. And so we know a lot about at least what we might describe as correlates of that rising inequality. And we also have lots of theory that might give us clues about potential causal factors. And in that discussion, technology looms very large. And so around theories of skill-biased technological change and so on. And correspondingly, we have a lot of empirics that give us intuition about the potential role of technology. So thinking about interpersonal inequality, we know from a huge amount of work by labor economists that since 1980, the occupational structure and the relative returns to education have strongly shifted in the United States and other countries as well, but here my focus is the US, towards activities that one might describe as being complementary to technological change over that period. And so we get computers and we see this sort of rise towards an occupational structure that complements that. Equally, thinking about interpersonal inequality, we know from a variety of relatively recent work that places that are more sort of invested in technological change, places that are more innovative as measured by patents, are more internally unequal. Okay, so we have that sort of pattern as well. We also have, of course, lots of ideas and empirics at the interregional scale. We know from Marianne's work with David Odrich and, of course, many others, that more innovative regions grow more than less innovative regions. And we also have the suggestion, at least, that new kinds of activities that emerge out of these technologies happen to be organized in highly agglomerated ways, which also suggests a pattern of interregional inequality. And this is, of course, just a brief summary of the things that we know about the potential role for technology in shaping inequality. The work that we are engaged in here is trying to address what we see as two big unresolved puzzles in that work. And the first puzzle is simply, we just don't know whether all technological change behaves equally with respect to inequality. Is any kind of technological change sufficient to generate inequality? Well, we don't know. And we don't know because, at least on the labor econ side, the work is really not focused on technology. It's focused on changes in the structure of the labor market. And it's sort of pre-assumed that skill-biased technological change is happening, but they're largely ignoring the technology side of the equation. It's just sort of imagined that that's what's causing it. There's some other work that chooses particular kinds of technologies and, let's say, measures investment at the firm level or the establishment level in computers, but that's sort of a very narrow kind of picture. And then there's sort of what I would describe as perhaps overly wide, that takes overall patenting as a whole and examines that, but doesn't sort of pick through technological change to try and identify whether there are particular features of technologies that generate this sort of creative destruction that we're interested in explaining. So that's one puzzle. The second puzzle is, as I hinted at, this huge volume of work about inequality is really narrowly, in fact, focused on the 1980 and beyond period. In other words, we see this rise in inequality in our societies. We get very concerned with it, and we study it only in that period, but we're, for the most part, ignoring the previous period, 1940 to 1980, in which we have this strong compression and convergence at the interpersonal and at the interregional scale. And we know during the 1940 to 1980 period, there's lots of technological change, and yet we have, for the most part, falling inequality. Now, one might respond to that by saying, well, there are, of course, many other factors that we think relate to inequality, and it could be those other factors and not technology that are dominant in that period. To which we say, well, that's all well and good, but we still want to understand, well, what is it? Why isn't technology dominant in that period? And what exactly is technology's relationship to inequality more generally? And so these are the puzzles that we're trying to fill. Or answer, I should say. So to try and answer them, we are trying to develop a theory that takes ideas that are not brand new by any means, but that sort of take ideas that economic historians, economic geographers, and others have been thinking about for a long time and put a different kind of spin on them and relate them more directly to inequality. And so, what we're interested in here is identifying features of technologies, ways in which technologies might vary from one another in a way that might matter for inequality. And so the first of those is that technologies can vary in terms of their tacitness. And so here I'm thinking, of course, many in the audience know what I'm talking about when I say tacitness, but for those who don't, thinking about the words of Michael Polanyi saying tacitness is when we know more than we can tell. And so this is the idea that ideas are, some ideas at least, cannot be rendered in terms of machines or coded in artificial intelligence or other kinds of routines, but are rather embodied in people. And of course, we can think about how this is related to interpersonal inequality in the sense that if you have new technologies that emerge, you will have rising demand for workers with the particular kinds of tacit knowledge that are required to work with those new technologies. We can't sort of instantly generate a supply of new workers like that. And so this imbalance between demand and supply leads to high relative rewards for those in the know. We can also think about the geographical dimension of this in the sense that when we know more than we can tell, the best way to try and tell is through co-located human networks. In other words, as economic geographers, we know that we get together in space to share tacit knowledge. And this could give this inequality at the interpersonal level a geographical expression. Another feature of technology that we're interested in distinguishing is technology's potential disruptiveness. And here we're sort of leaning on ideas that come from economic historians. And I really like Joel Mokir's very sort of evolutionary language around around mutations that generate entirely new species that set the economy on a new path. And so here we're thinking about sort of general purpose technologies linked to industrial revolutions. And you can see how to get inequality, it seems that you need both of these things in the sense that there are many things that are going to be tacit, but are not necessarily highly valuable in the economy. And equally, there could be things that are disruptive, but if they are not very tacit, well, then that disruptiveness can be channeled sort of directly into automation. And we think that these features of tacitness and disruptiveness are likely to be expressed in a very sort of geographical way, meaning that we're going to have this sort of rise and fall of concentration and dispersal. To give you a sort of a very crude kind of rendering of what we're thinking about here, we can think about these sort of major technology shocks, industrial revolutions, producing this sort of dense concentration of tacitness and disruptiveness. And then at a certain point, that sort of shifts to something else, and we get a decline in inequality. And then we get another sort of big technology shock, and with it, a sort of a concentration of tacitness and disruptiveness once again. And this sort of pattern, we think, helps us also think about the patterns of inequality that I showed you in the first sort of substantive slide. Okay, so this is kind of what we're after here. So this generates some real challenges. In other words, how do we try and chase this down? Well, if we want to try and chase it down, we need to generate measures of tacitness and disruptiveness for individual technologies, but also for the whole sort of scope of technological activity, and also to do that over the very long run, right? If we want to try and sort of match our labor market empirics. And so, of course, people have been thinking about tacitness and disruptiveness for a very long time, but we don't really have measures at scale and over the time period that we're interested in. And so we need to try and fill that gap. And to do that, I'm going to talk about work that we're doing that makes use of machine learning techniques and high dimensional data coming from the USPTO and also from Google Books. I'm going to try and also do a bit of description of what these measures look like once we build them. And then eventually, although it's not going to be in today's presentation, eventually we want to formally relate measures of tacitness and disruptiveness to our labor market data that I showed you at the very beginning. Okay, but that's not coming today. All right, so let's talk about our attempts to measure tacitness here. The intuition here comes from, of course, the great wealth of writing about tacit knowledge. And from that, we're sort of boiling down some basic intuition that tacitness and codification represent poles in a kind of a spectrum or a continuum, first of all. And second of all, that in a general sense, we expect there to be a temporal pattern from very new technologies being more highly tacit, and then them eventually moving towards greater codification. And of course, this is a simplification, and we don't necessarily expect linearity in this process across all technologies, but it's a generality that is present in the literature, and it's one that we are building on. What we're doing here is we are leveraging very rich information in Google Books, corpora, and the USPTO. And what we're doing to start is to count every single word in Google Books as corpora. Okay, so for those who maybe don't know, and probably most of you do, Google Books has been scanning millions and millions of books. These contain, of course, trillions and trillions of words. And so what we're doing is we are just counting all of the instances of all of the words, every single word in all of the Google Books corpora. So with the idea being that words that are mentioned more over time, well, this indicates greater codification of the underlying ideas, whereas words that are mentioned less are going to be more highly tacit. Okay, so we do all of that, and then we match all of these words to the universe of patent descriptions in the entire length of the USPTO patents from 1836 up to 2010. And of course, for those who are less familiar with patents, patents contain, among other things, often many pages of description that talk about the particular invention. Well, we're matching those books from Google, words from Google Books to those patent descriptions. And then we are aggregating up to the level of patent classes. So we are measuring tacitness for each patent class, and a patent class will be more tacit if it contains patents that have words that are on average less commonly mentioned. And conversely, it will be a more codified class if it contains words that are mentioned more often. Okay, so just to give you a bit of proof of concept here, consider here two particular patent classes. compound tools, which is in the mechanical category, and information security, which is in the computer and communications category. And you can see the sort of time path of the frequency of keyword appearances. And what you see quite clearly is, and compound tools, we're talking about screwdrivers and hammers and stuff like that. So we see very clearly that the sort of the time path and the absolute frequencies are quite different for these two classes. The one that's obviously a much more recent technology, we see that the words only start to rise in frequency around 1970 or something like that. Whereas we see a very different sort of pattern for compound tools, and one that we think lends some support for the approach that we're taking here. Okay, so here's some more descriptives of our tacitness measure. So what we're doing here is just grabbing the 7 most tacit patent classes and the 7 least tacit patent classes over the 2005-2010 period. Just again, to sort of do a gut check and see if we are headed in a crazy direction or maybe a good direction. And so the top 7 here, it makes some sense. There's some biotech stuff, some electrical and electronic semiconductors, some computer stuff, and so on. And again, 2005, 2010, so not today, but close enough. And then at the bottom, we see some stuff about railway technologies, book printing, and so on. So at first blush, at least, we get results that broadly make sense and confirm our the generality of our approach. Oops, jumped a bit. Okay, so we've got a measure of tacitness, and we've got some alternative measures too that you can ask me about at the end if you like. Next, we want to measure potential disruptiveness. And here we're leaning on work that has been led by Sergio, my collaborator, who's published just recently, in fact, a paper bringing some of this work together in research policy, where essentially we're leaning on ideas that come from economic historians' study of general purpose technologies. And from that work, sort of boiling down 3 particular characteristics and measuring them in order to, again, classify patent classes on the basis of their potential disruptiveness. So the first is that disruptive technologies should evolve rapidly. They should have a wide scope for elaboration. And so here we're simply counting, calculating the growth rate for each patent class. That disruptive technology should be widely adopted and widely used by other technologies. And so here we're simply, again, using the patent descriptions that you can see here on the screen to find keywords that are specific to the use of particular other technologies, and then just count the number of classes that mention a particular technology's keywords. One that gets mentioned more often, well, this will have a higher use complementarity. And third, that disruptive technology should have high levels of innovation complementarity, meaning not just that it's used by other technologies, but that it enables innovations. And so here we are measuring co-occurrence across patent classes. And so saying, well, a patent has, or a class rather, has high levels of innovation complementarity if lots of other classes outside of its category are co-classed with it. And so here again, we are measuring, we are sort of ranking technology classes, patent classes, on the basis of their potential disruptiveness. Here's another descriptive table that gives us the top and bottom 7, so most potentially disruptive and least potentially disruptive over the 2005 and 2010 period. And again, we get some fairly reasonable kinds of technologies. Computer stuff, things that look like mobile phones, storage, and so on. And then at the bottom, some heating systems, some basic chemical stuff, explosives, and so on. Okay. We can also assign these to places. And I should say, really what we're doing here at the most basic level is we're not necessarily sure that one that scores 1 point above in tacitness or 1 point above in disruptiveness is necessarily more disruptive or more tacit. We're simply just dumping classes into above the median in disruptive or below the median, just for maximum contrast here. We're being very simple. Later you can get down to the level of patents or inventors or locations and so on. But right now we're staying very, very basic. Here's a table of, if we just look at places that have the most disruptive, most activity and disruptive classes. And so this is a logical group. Of course, it would be different if we scale it per capita. But anyway, this is just sort of meant as an illustration. We get a sensible set of highly disruptive places for the 2005-2010 period. Okay, so we are now armed with some measures of potential disruptiveness and tacitness. And what we want to do now is take this back to the original stylized fact. And what we expect is to observe certain kinds of patterns in the evolution of tacitness and disruptiveness. And so what we see, in fact, and this, to be fair, was a bit of a surprise for us, is patterns in tacitness and patterns in the geography of disruptiveness that very, very closely mirror the patterns of wage inequality that I started with. And so the wage inequality picture we see in panel A. In panel B, we see that the spatial concentration of tacitness proceeds in a dimension that between 1940 and 1980, tacit technologies are spreading out over space, kind of doesn't matter how we measure it. And then right around 1980, we see a reversal, and tacitness starts to strongly concentrate in space. In panel C, looking at the geography of disruptive technologies are potentially disruptive technologies are spreading out between 1940 and 1980 across the landscape of the United States. And again, we're looking at commuting zones here, just to remind you of the geography. Then right around 1980, we see a reversal in the geography of disruptive technologies, such that these disruptive technologies also start to strongly concentrate in space. And I want to emphasize that panels A, B, and C are representations of very, very different data sources, right? Panel A is labor market data from the census. Panel B is a combination of Google Books to get the vocabulary and then just patent descriptions. And panel C is a combination of different kinds of patent information, especially around classes and the relationships between classes. So these are very different data, and yet they tell a story that we think is strongly consonant and one that sort of pretty closely fits what we imagined. So we were, let's say, pleasantly surprised when we saw these pictures for the first time. Briefly, we can also do a little bit more exploration of the correlation between tacitness and disruptiveness. You might be asking, well, are you sure you're measuring different things with tacitness and disruptiveness? And one way to look at that is to look at their spatial correlation. And what we see is that, in fact, between 1940 and 1980, places that are doing tacit stuff are not places that are doing highly disruptive stuff. In fact, if you think about the confidence interval here, for a good chunk of the 1940 to 1980 period, that confidence interval crosses a correlation of 0. And then right around 1980, you get this sharp uptick. And between 1980 and 2000 in particular, you see that the places that are highly engaged in tacit activity start to become also the places that are highly engaged in disruptive activity. And if you look at the numbers on the y-axis here, you can get a sense of just how big a change this is. We can also explore, and again, right, we're in the realm of exploration here, right? We want to sort of check our instincts and see if things generally hold together before we start running regressions of stuff. So here on the left two pictures, we see explorations of the correlation between places that are specialized in either tacitness or what on this picture is called frontier technologies, but that's just disruptiveness before we decided what to call it, and interpersonal inequality as measured by the 90 to 10 wage ratio. All right, and what we see is that for both places that are specialized in frontier activity, disruptive activity or tacit activity, those that are more engaged in that in 2010 are more internally unequal. And those that are less engaged in it are less internally unequal. But in 1960, we get the opposite pattern, right? In the middle of this wage compression period, in fact, places that are more disruptive and more tacit are less internally unequal. So there's a sort of very strong reversal there. On the right-hand side, we see a couple of scatter plots that do the same thing, except instead of looking at internal inequality, we're looking just at average wages, which is, well, one way we could think about overall sort of interregional inequality. It's not the only one. And here we see not exactly the same picture, but nonetheless a differentiated relationship such that places that are most focused on tacit and disruptive technologies have higher wages than those that are less focused on that stuff. In 2010, it's also true for 1960, but it's a weaker relationship. So that's kind of where we are, and I want to close up and hopefully get some questions. So just to summarize, there's a growing consensus that technology plays a really important role in the recent post-1980 rise in inequality. But there's a really, I would say, a lot that we don't know about this relationship. The work that we're trying to do tries to answer a couple of questions, or at least hopes to do so in the future. First of all, does all technology produce creative destruction, or as a corollary, are there particular characteristics that are associated with this sort of inequality producing creative destruction? And second, what role is there for technology when we are focused less myopically on the 1980 to the present period, but also thinking about the prior period, a 40-year age in which technology, lots of technological change was happening, and yet inequality was falling. We are hypothesizing this sort of center of the Venn diagram kind of role for tacitness and disruptiveness, and also that that this happens in a particular geography. In other words, that the geography isn't just sort of a byproduct or something that we think of later in thinking about inequality, but in fact that its spatiality is central to our understanding of both the interregional, obviously the interregional, but also the interpersonal. And so we're developing measures that try and capture tacitness and disruptiveness so that we can explore this. And what we found so far is that the spatial patterns of tacitness and disruptiveness over this 80-year period strongly mirror the patterns of wage inequality between places and within places. So of course we need there's lots more to do. We need to think about other factors beyond technology. We need to, of course, think about regression. But at this point, we're just sort of playing around, but we think it's sort of suggestive playing around. And there's lots more to do. And as I said, we're starting with this very sort of crude setup, but we have very finely grained data, right, at the level of individual patents, inventors, and so on. And so we can, once we have a firmer sense that we're headed in the right direction, can really dig down and have much more fine-grained understanding of what's happening. So hopefully I'll get a chance to tell you where we're at next time. But in the meanwhile, thanks very much for listening.
And let's see, Tom, that was just terrific. And so again, in both of these papers, we see new measures, which is really exciting to increase our understanding of these phenomenon. So Tom, there are some questions that have come up for you in the
Great.
chat.
Great. How do I do this? Do I just look and there's a Q&A thing here?
Right, that's where it is. And so,
okay. So let me just take a second and read that. Measuring, yes. Does everybody see the Q&A questions? Or is that just something that I can see?
I think everyone should be able to see them.
Okay.
Okay. Yes, and the concept of tacitness and the sort of technical terms and.
Well, yeah, I mean, so I think the thing is of course, these patent descriptions have an enormous amount of text and lots of different words. And what you see is that I mean, in the sense that the technical words are the ones that are the most useful. I mean, all patents have the word the and all of that kind of stuff. But you see very clearly that this sort of differentiation according to the particular vocabulary that a patent text has. I mean, so of course, the number of mentions isn't the only way that we could think about capturing this kind of thing. And we've done a bunch of work where instead of looking at the frequency of the vocabulary, we have also looked at the moment at which a word appears in Google Books. And equally, we can also look at the moment at which a word first appears in the patent corpus, let's call it. And so we've done all of these sort of variations, and they tell relatively similar stories. And so I'm not sure that we've necessarily settled on the best version of this yet. And you can tell from the way that I talked about this very sort of crude, you're tacit if you're in the top half, and you're not tacit if you're in the bottom half, that we're starting very modestly, let's say, right? That we're not necessarily convinced in the sort of micro differences between, one that's slightly more tacit along our measures than another. We're trying to look at this very sort of crude margin of the sort of the most obviously tacit and the least obviously tacit. And what I didn't show you is in the picture where I had the three panels, and we're looking at the evolution, let's say, of spatial patterns of tacitness. If we did the same picture for the least tacit 50th, the bottom half, essentially, what we think is suggestive is that bottom half looks completely different. And you get the same thing with disruptiveness, meaning that at this very crude kind of scale, we can see that at the very least, more disruptive and more tacit technologies behave in space very differently from what we think of, what we can be confident of as being less disruptive and less tacit.
So Tom, I think it's so exciting because we talk a lot about tacitness, but we've not mentioned it or measured it. And I think there's also an opportunity to see, and this is Patrick's question, when do terms go from being tacit to being then so codified that they're well accepted? I mean, that's another consideration. We also have a variety of questions, including, Nicola and then Pedro, where there is a sort of need to look at the institutional factors, and we have a declining protection, declining unionization in the United States, and then wage legislation, and so this is
I mean, so yes, absolutely. And we every time I've talked about this work, everybody, of course, very rightly raises these questions, and they are absolutely the right questions. I think they are, here's what I'll say is, empirically, we are, I just finished building a data set that captures changes in, marginal tax rates at a state level, and changes in unionization, and changes in the minimum wage, and all of these other kinds of competing causes. And I think, eventually all of this will end up in regressions. But I also think that these things are not, I mean, these are endogenous complex relationships. And I think Cesar made a good point in his talk, referring to the coevolution of institutional structures. And he was talking about sort of productive structures, but also technology structures. And so I think we are in a place where, from my perspective at least, it is very hard to completely disentangle changes in technology from changes in institutions. But well, we're going to try our best, and we'll see what happens.
Right. No, always, lots more work to do. And so I've just learned that people cannot see the questions. And so I will then try to answer them. And so Frederick asks the effect of technology as the state of technology developments, rather than the nature and uses of the technology. And, so now we have a lot of focus on surveillance and control with our technologies, which is going to be less productive.
Yes, yeah. So I mean, it's a good question, I think, and partly I feel like partly this is we're maybe guilty of thinking about what we can measure as being what we end up chasing down. And I know, Marianne, you've talked lots about that, but we have these incredibly rich information about patents, and with this sort of emerging capability to make use of machine learning tools to mine that and extract meaning from it. I've never really been a patent guy, and so this is sort of me guiltily being like, okay, well, this stuff is there and it's very rich, but I think there are dangers too in conflating the production of technology in as much as patents even capture that, and the uses of technology. So I do take that point, and I think I don't have a perfect answer, but I'm certainly sensitive to it, and we're thinking about it.
Great, very good. And Simona mentions, and I think a lot of us now are using patents, and we are using text mining. And so the question is, would it be useful for us to have some shared repositories for data, and then also, sort of a GitHub with different code and things for this community to advance our work? And so suggestions like that are appreciated. Tom, please.
Yeah, no, I think that's a great idea. I mean, we are going to, when we get a bit further down the road, you can see that we're still in a pretty exploratory stage, but we will of course we want to share all of these measures so that people can make use of them. Because there is, especially the tacit stuff, I mean, there's a universe of talk about tacitness. So, to be able to measure it and apply it to people and places and technologies is, I think, opens up, potentially, if we really are onto something, opens a lot of doors.
What a great session to start this workshop. And so, Cesar and Tom, thank you very much. I want to stick to our schedule. Let me mention, we're going to take a 15-minute break, and so resume at 1:45. Make your own time zone adjustment. And let me just forecast that in the next session, Frederick Guy is going to be talking about monopoly and financialization as a cause of income inequality. And Neil Lee is going to be looking at inclusive innovation and what the literature has told us about how that affects income inequality. So, wow, we are off to a great start. And so thank you so much for your participation. And we'll see everyone in 15 minutes.